Alright, what's up guys? We're back with another video. Today we're doing 987 vertical order traversal of a binary tree. So let me select the red color. And this is actually a hard question, so a lot of you might be worried like, oh no, a hard question. I've never done those before, I don't want to, but I'm going to show you that they're not that bad. They're actually pretty easy. You can end up happy like this guy right here. So let's look at the actual problem. Um, Given the root of a binary tree, calculate the vertical order traversal of the binary tree. So each node has a position, row, and column. And it gives definitions for the left and right, how they're calculated. The root of the tree is at 0, 0. So we see that the row is basically always increasing as you go down, so the row can be synonymous with the level you're at. Level 0, level 1, level 2. Alright, that's easy enough to follow. So the row, we can write that row is equal to level. And then the column is defined by if you go left or right. So if you go left, you -1. If you go right, you +1. So you could go right and then left, and then +1, -1, and go back to 0. So if we check, let's see, column negative, for column number -1, we have 1 value. For column 0, we have 2 values in this case. And for column 1, we have 1 value. Column 2, we have 1 value as well. So the vertical order traversal of a binary tree is a top to bottom ordering for each column index starting from the leftmost column and ending on the rightmost column. So leftmost -1 to 2, so increasing order. There may be multiple nodes in the same row and same column. In such a case, sort these nodes by value. So this is a lot of information. Let's try and break it down. So we know we have to do increasing order for columns, and we want it to be top to bottom. So top to bottom has to do with level, which is just row. And top to bottom, it goes from 0 to increasing values, so 0, 1, 2. So both the column and row are sorted by increasing value. And basically you want to sort by column, and within that sorting you want to sort by row. So over here you can see that 9 corresponds to column with the value of -1. 3 and 15 correspond to columns with the value of 0. 20 corresponds to columns with the value of 1, and 7 corresponds to columns with the value of 2. And we choose 3 before 15 because 3 has a row value of 0, while that's not row, that's column. 3 has a row value of 0, while 15 has a row value of 2. Okay, so that's great. What we're sorting by first is by, let's do a different color. We've been using red a lot. First, we sort by column. Then we sort by row. And then there's an interesting case they gave. If it's the same row and same column. So when does this happen? Let's say this case, for example, 21. In this, we increase the row by 1, so it's at row 2. And since we went right after we went left, so -1 plus 1, because we're going right, we have 2, 0. So here we have the same row and the same column. And in this case, we want to sort by value. So great, we got the first part of the question done. We want to sort by column, then by row, then by value. And this is in order to return lists of all the values in one column. So column -1, column 0, column 1, column 2. Now let's move on to the second part of this problem, in my opinion, which are calculating the bounds. One sec. Let's take there. The bounds. Okay, so what are the column bounds right now? We don't know. We have to find a min and a max because we don't know how big the tree is given by the root node. So in our search, whatever search we do choose to use, we have to keep reference to the minimum value we see in terms of column and the maximum. And then for row, we know that we start row is synonymous with level, so the min value is 0 and it's always increasing, row plus 1. So we have to find the max value. So these are the bounds for our column and row. For value, we can sort simply by using the built-in functions in whatever language you're using. So in this case, what are the min and max that we find for each of these? We find in this case, it's -1 and 2. And for what's it? The row, it's 0 and 2. This will become important because once we organize all these points into a better data structure, knowing the bounds will help us search through to add the values in appropriate order. So on that note, let's look at the data structure we're going to use. Right now, let's just call it a table. So in this table, we have column, row, and we have a list of values. So in sorted order, let's see, column number -1 has a row number of 1 with a value of 9. Column number 0 has a row value of 0 and 2. So there's 2 rows with the column number of 0. So it's 0 and 2. For 0, column number 0, row number 0, we only have one value, which is 3. For column number 0, row number 2, we have two values, which are 21 and 15. 21 and 15. So we can continue this process real quick. My mistake. 1, 20, and 2, 7. Alright, so the next thing we would want to do is we want to use our sorting methods that we've determined before. So it's our first thing, second thing, and third thing to actually figure out how to calculate what our output is. So we know from before that we want to merge all the columns into one. So all the columns of a single value, so we want to merge into one. So here we have 3 and 15 because they're both in column of 0. And we know if they have the same column and same row, we want to sort them. So if we go through -1, 1, 9, that simply becomes 9. 9. This we go through, we go to column 0, row 0. First value must be 3. Column 0, row 2, we want to sort these values and add them in. So it's 15 and 21. Then this is simply 20 and 7. And here we have our output, which is a list of these lists. So now that we know how we're going to get our solution, we need to know what kind of data structure we want this table to be. So the most optimal data structure would be a map because we are searching from our bounds for values. So it would be a map of integer. Second value would also be a map of integer and a list of values. List of also integer. Yes. And we can see this is the columns. This is the rows. And this is the values. So in this example, we can break it down further to show you a more like clear way of how we're using these bounds. So let's go back to our green. Our column bounds are, row bounds are -1, 0, 1, and 2. Our row bounds are 0, 1, and 2. So if we want to do this implementation in order, like making our vertical order traversal, we start with our min and we iterate to our max. So this is basically a for loop. And this is also a nested for loop in this one. So we start at -1. What values do we have? We search for 0, we find nothing. We search for 1, we find -1, 1 has value 9. Nothing. So we add 9 to our output array. And then we search for 2, we have nothing. So 9 is our output array for column number -1. See that? I don't know if I mentioned this before, but we're using a hash map because they have really good lookup times. It's constant lookup time. And let's go to a more interesting example, which is what happens when we reach 0. So column number 0 can have row values of 0, 1, and 2. So 0, 0 has a value of 3. So we want to add this to our output. Then 0, 1 has no values, and 0, 2 has 2 values, so 21 and 15. So we want to sort these and add them into the list. So sort it, add them to the list. We get 15 and 21 for column number 0. And we just continue this process until we basically do what we did over here. So that's why the bounds are necessary. They help us figure out how we're going to iterate through all our values and generate our output. Alright, so let's clear this up a bit and let's do a little TLDR. So the steps for this question are, we need to convert this tree into a more manageable data structure such as this map. And we need to calculate these bounds and use both of these to generate our output. And that's basically the entire question. So we first figured out what's our sorting methods, what are the bounds for these sorting methods, and what's the data structure that we can use for these bounds. So the problem was broken down pretty simply. Like, it looked pretty complicated when we first saw it, but once you broke it down, it became a lot more manageable. So time and space complexity. Time complexity, we're going over all n values, where n is the number of nodes. So n is equal to number of nodes. We're going through the tree once, then we're going through the map, so n plus n, O of n. Space, O of n, because we have to generate our map. And that's basically the space and time complexity. Now we can actually look at some actual code so we can understand how this looks in implementation. It doesn't matter what language you're using, because it shouldn't matter. It's just syntax. What matters are the ideas I explained before. So over here we have just an array to calculate our bounds, to hold our bounds. And we have our depth first search over here where we go through the tree. And we have three cases for new values. If the column isn't present, we want to add the column, row, and value. Row isn't present, add the row and value. And if both are present, you just add the value to the list of values. Then we just want to update our bounds for max and min if we do want to update. And we want to do a depth first search. So search the left and search the right. And if you remove all this processing, so this is for generating our graph, this is for updating the bounds, we see that this is like this looks exactly like a super simple depth first search. So that's exactly what this problem was, a depth first search. And then once you have these values, you want to iterate over the columns, so from the min to max, over the rows, the min to max, and sort the values if you need to. So that's the whole solution. You know, it looked a lot more complicated when you were first looking at the problem, but now you see it's easy. You can end off as a very happy coder that you didn't have to just struggle through this with the interview. With a lot of these problems, you just have to break them down, and eventually you'll find the solution. So you can talk to your interviewer to work it out. So that's all for this video. Please like, comment, subscribe. I really appreciate it. And also the code will be in the description. The link to my GitHub post, not my GitHub post, my Leetcode discussion post will be in the description. So please like that as well. And I'll see you guys in the next video. Bye.